So the problem I'll be solving is problem number 2 because my last name starts with an E. If I made a mistake into the first name, that should be fine because my first name also starts with a J. So it's number 2 either way. But anyway, so to solve this, we begin by checking P of x and Q of x to see if the functions are analytic. So the way we do that, first obviously we need to take P of x and Q of x. So in this case, P of x is equivalent to 3 of x, and then we want to divide it by the leading coefficient, which is this x squared plus 2. So 3 of x over x squared plus 2. And then Q of x, in this case, Q of x is going to be -1, as you can see here. So, 2. And then, with this, we can see that if we plug in 0 as our ordinary point, we see that these are analytic functions. So we can go ahead and solve like this. We'll first start by taking the power series as our solution y. So first we have y equals the sum of n from 0 to infinity, and that'll be constant of n times x to the power of n. This is the power series. We can derive that to get, let's do it this way. Deriving that, we get the power series from n equals 1 to infinity. And then the derivative of that would be, once again, the constant, that doesn't change. It'll be times n because of the power rule, times x of n minus 1. And then if we continue on our second derivative, since this is a second, we also have to solve for y double prime. We n equals 2 to infinity, of n, n, if I'm not mistaken, should be n minus 1 times n x to the power of n minus 2. Okay, and then from there, we need to start plugging into the equation. So first we can actually rearrange the original differential equation that we have. So let's use another color. Let's see. Let's just get this all separated out. So if we reorganize our original equation, I need to make sure I don't. Okay. So we have our leading coefficients here. Sorry, leading coefficient. We've derived our solution y. So we'll continue on. First, before we plug into the equation, we can actually rearrange it. So to do that, let's first distribute x squared plus 2. So we have x squared y double prime plus 2y double prime plus 3xy prime minus y. Sorry. And then that all equals 0. Now, let's see. We can go ahead and plug in our solutions. So we have, this will be a long one, x squared color code this. Just we have x squared. Okay, let's actually go back. So with x squared, if we're going to multiply it by this function here, we can actually just cancel out the x squared with this, because we have if we have n minus 2 and 2 as our exponents, they actually cancel out. So we would end up having, let's see, sum from 2 to infinity, Cn n minus 1 times n x to the n. Then we would put all in parentheses. Then next we have power series n equals, once again, n equals 2 infinity. And then this time we're plugging in 2. Not much you can do to cancel out. So we have times constant n times, let me make that a little more clear, Cn n minus, sorry, n times n1 times x 2 and 2. Might need a little more space for this. So let's keep plugging in. Now we have power series. Power series from, I believe it's n equals 1, plugging in y prime to infinity. Then we're plugging this into, we're multiplying this by 3. Oh shoot, it should be 3xy. So this is going to be 3x times c of n times n, and then the x actually cancels with the n again, so we end up with x to the n. Actually, now that I think about it, I think I might have made a mistake in the work I did previously. I believe the n should not, sorry, the x should not be here. Okay. Now we find, then we just have y, which is minus sum from 0 to the Cn x to the n equals 0. Right, moving on. We need to, before we can combine like terms, we need to make sure all the power series have the same exponents. So we can look here, sorry, we need to find a way to combine the series. So we can see here, if we plug in the n's, we have, see, if we plug in 2 here, we have, let's see the difference. Here we have, let's take up too much space. Here we have squared, here we have 2 minus 2 is 0, x is 0. We have 1 plug into n, so x to the first. And then we have, once again, x. So x to the 2 is our highest exponent, so that's going to be our baseline. So we can start rewriting this equation based on that. So we start with n2 going to infinity. And then now we're going to rewrite the equation a bit. So we still have Cn times n minus 1 times x n. All right. And then let's see. Plus, if we plug in 2 to n times n minus 1, we end up getting 2 C2 2 minus. And then if we do the math there, we're going to end up with 4C2. Double check, that's 2 minus 1 is 1, times 2 is 2, times 2 is 4. So 4C2. And then if we try to plug in n equals 3, we end up, because we do want C3, so we can get more instances of the power series. We get do similar math, and we get 12C3. Okay. And then we tack on the x at the end since it's the next in the series. Now we have so this one is going to be rewritten later, but for now we have the next term. It's going to be if we're going using 2 as our highest exponent, we're going to try to get this x to the n minus 2 to actually be 2 as opposed to 0. So we're going to go with the series from n equals 4 to infinity. We're going to end up with 2 times Cn times n x and 2. And then from there, we're going to do the same thing we did before. So we'll end up with plugging in 4. We're going to end up with 3. Actually, my bad. We're not going to do it for that one. We're going to move on right to... Actually, no, that's my bad. It's going to be for this one. But if we plug it in, we get 3C1 of x. And then if we move to the next term, we have x of 1. So we want to change that to n equals 2. So 2 to infinity, as usual. We have 3 n x minus d0. That would be coming from here. So we plug in 0, c0, x is 0 is just 1. So that's all that is. And then if we change that to 1, then we get minus, and then we plug in 1 instead. We get c1x. And then we can end off with this last term. It'll be minus power series n equals 2 to infinity Cn x to the n 0. And then we want to look at this term in particular because there's a certain way we can this term right here can be rewritten a certain way. So we can expand it such we have, we have the power series. This is so we can get to n equals 2. So we have n equals 2 infinity 2 Cn, and then we're gonna take move the n plus 2. We're gonna compensate to make this match. So we'll have n, instead of n, we'll have n plus 2 to cancel it out. And then once again, n minus plus 1. Yeah, it'll be n plus 1 in this case. And then we'll have x to the n. Then that'll go into the final equation. But actually, as I keep going, I'm going to combine like terms. So let's see. First, we have C2. We want to look at everything we have at C2. We only really have 4C2. So we'll go with that. 4C2. Using up too much space. Let's go a little lower. Or C2. Okay. 4C2 minus, let's see, we have C0. We can get rid of that. So C0. We also have all the values. So those are all our single constants without x. Now we have the values with x. So we have, let's see, I believe we have 2. So it'd be 12C3. There should be one more. There. That is plus 2 D1 X. Add on everything under a sum of 2. We have n equals 2 to infinity. So we end up with, let's see, if we combine all our like terms, we get 2 times Cn plus 2 times n plus 2. Oh, sorry, I forgot to mention this n here, n plus 2. I forgot to add that. So that's why we have Cn plus 2 here. N plus 2 times n plus 1 plus, so that's what we have here. To the n, so we can get rid of that. Plus Cn. These are all the values with Cn tacked on. So we have n squared, leave squared. So for part of this, we're actually we are combining like terms as it is. So n squared minus n plus 3n 1, just to save space. But to explain why we have n squared, we're already combining like terms with this one. We have an n times n minus 1, so we wanted to combine that. I believe that should have been here. Then we have 3n, and then we have minus right there. Okay, so that all is equal to 0. And then we are going to be able to use various pieces of this. We can use to actually solve the rest of the values. So a little more space here. moving forward, more space here. Okay, so we can start with 4C2. Running a little too big. Let's see. 4C2. That'll be minus C0. That's our term here. This equals 0. So if we rearrange this, we get C2 equals C0 over 4. We also have this term, 12C3 plus 2C1. Rearrange that. We get C3 equals minus C1 over 6. All right, then we have this entire term here within the power series. So to solve for that, we have, let's write it out first. We have 2cn plus 2 times n plus 2 plus cn times n squared plus 2n minus 1 equals 0. And then the 2n comes from combining 3n minus n, so that makes it a bit simpler. Now if we rearrange the equation, we get cn plus 2 is equivalent to minus cn times n squared plus 2n minus 1. That goes all over 2n plus 2 times n plus 1. And then n in this case is a power series, so it can go, it has a minimum of 2 as we established earlier, but it keeps going onward one by one all the way up to infinity. So if we want the first two solutions of the series, then we would solve for n equals 2 and n equals 3. So to do that, we simply plug in. Let's use a different color. All right, so for n equals 2, have Cn equals, let's see, C2, if we plug in 2 here, we have 2 squared is 4, 4 plus 2 times 2 is 4, 4 plus 4 is 8, 8 minus 1 is 7, so minus 7 C2. That's going to be all over 2 plus 2, 4, 2 plus 1, 3, 4 times 3 is 12, 12 times 2 is 24. So it would be 4 times 3 is 12. I might be missing something here. My work says 96. Ah, okay, I see. So we end up with 2 plus 2 is 4. 4 times, and then 2 plus 1 is 3. 4 times 3 is 12, times 2 is 24. And then if we substitute C2 in, if we recall, C2 is C0 over 4. So because we want to have C0 first. So if we have that, we have, plug that in, we get minus 7 C0 over, so 4 times 24, that's, if off the top of my head, that's 96. And then we can do the similar procedure for n equals 3. 3, n plug in 3, we get minus 14, 3 over 2 times 4 times 5. 5 times 4 is 20, times 2 is 40. Multiply that by 6 as we see here, and also negative. So this is essentially equal to minus 14 d1 over 2 times 40 times 6. That's 6 to 12. 240. You can divide that by 2 to reduce this fraction, and we get 7c1 over 1. And then that is, all right. Now, our final solution, we get that by combining all the terms we have with constants. So let's see. Base, and then write this all out. I'm going to go back to like dark blue. Sorry. Okay, so our final solution, we plug all this into the power series. So y equals, so C0 is just that, C0. Actually, no, let's go, we'll go one by one. C0, actually, this is, there's gonna be more simplification to do after, so let's use a different color. Actually, we'll just stick with blue. So C0 plus y equals. So this is the basic form of the power series. C0 plus C1 x plus C3, in other words, C0 over 4 x squared minus C3, in other words, C1 over 6 x to the third times C4, which we have established through, because if we have this, sorry, this is n plus 2. So n plus 2, if it's 2 plus 2, that's going to be C4, and then this will be C5. So C4 in this case would have been minus 7 C0 over 96, and then C5, oh, times x to the fourth, and then C5 would have been 7 C1 over 120. And then this continues on and on infinitely. So if we combine like terms, let's see, we get our final answer. So we have for C, so this is all in terms of C0 and C1. So we take all the terms, so we have y equals, that y a little nicer. So yeah, start with C0, and in parentheses we can put in 1. Plus, next we have 1 over 4 x squared the more I zoom out, the thinner my writing gets. Squared minus, next term we have is 7 over 96. x to the fourth. Then, oh, sorry. We have plus this will all be added to C1. We have, so in parentheses we have x, and then next we have minus 1 over 6. Third. Plus, we now have 7 over 120. 7 over fifth. Forgot to put the x to the fifth here, actually. And once again, an infinite progression of sums. Then, in terms of finding first few values, this will be our final answer to the power series of the equation x squared plus 2y double prime plus 3xy prime minus y equals 0.